All right, this is our lecture for section 8.6, and this will be split up into two sections. So this is lecture 8.6a. The essential standard is I understand normal distributions and can calculate and interpret z-scores, which we won't do today. But we will understand normal distributions, and I can calculate probabilities for normal distributions. So in statistics, there's a special density curve called normal distributions. Okay, we've been talking about distributions of data. We've been using histograms and box and whisker plots to look at distributions. A normal distribution all have about the basic shape, same shape. And this is called a bell-shaped curve. So here is my bell-shaped curve. And so this would be my normal distribution, and where it gets that name, if you can imagine a little bell ringer underneath that, that would be a bell, okay? They are described by their mean and standard deviation. When we have a normal distribution, we are going to talk a lot about their mean. And so this mean is mu. And so there is the mean of a normal distribution. And we have a standard deviation sigma. And that sigma location is approximately right where the inflection point is located, where the curve goes from concave up to concave down. And so this is one sigma away from our mean. The mean shifts, okay, so that is a distance of 1 sigma. The mean shifts the curves right or left, and standard deviation measures its spread or variability. Remember, standard deviation is a measurement of variability. The mean is located at the peak, like I showed you, and the distance from the mean to the point on the normal distribution where the curve changes from falling more rapidly to falling less rapidly, which is an inflection point, okay, is considered 1 sigma, okay? These curves are important since many statistical distributions, test scores, for example, measurements, closely match this distribution. Even though many distributions do, some do not, such as income distribution. Income distribution might look something like this, where we have a lot of people that make a little bit of money. We have a few people over here that make a lot of money. And so that would be a situation where we do not have a normal distribution, all right? I'll let you read this, but I will say the total area under the curve is represented by 100% of the data. So the total area is represented by 100% of that data, okay? All right, let's talk about this empirical rule. Normal distributions, and you need to memorize certain things about this. I'm going to tell you, normal distributions obey the 68, 95, 99.7. This is called the empirical rule. Okay, what does that mean? Okay, what that means is that approximately 68% of the data falls within 1 standard deviation. So once again, here is my mean. This is my mean mu, and 1 standard deviation would be to approximately this inflection point. So here is 1 sigma, and this is the area underneath this part of the curve represents 68% of the data, okay? Approximately 95% of the data fall within 2 standard deviations. So now I've gone another sigma over. So I have gone a total of 2 sigma to the right. And I have gone over an additional 2 sigma to the left. And now that represents, let's use a light blue. This area will represent 95% of the data, from 2 sigma to the left all the way to 2 sigma to the right. And then lastly, I have 97% of the data that is between 3 sigma. You can see the 3 sigma right here. This is mu minus 3 sigma. This is mu plus 3 sigma. That will represent, if I go and shade all of that area, that represents 99.7. So I believe you need to remember this: 68%, 95%, and 99.7%. This is 1 sigma, 2 sigma, this is 3 sigma, okay? All right, so let's see how we can use that information, this empirical rule, to calculate some things. All right, so number 1, the heights of 1,800 adults are normally distributed with a mean of 68 inches and a standard deviation of 2 inches. What percent of these adults have heights between 68 and 72 inches? So let's go ahead and draw our normal distribution. They told us that with a mean of 68 inches. So I know that my mean is 68. I know that my standard deviation is 2 inches. So if I go over to 1 sigma, that is going to be 68 plus 2, so that is 70. If I go over to through 2 sigma, I add another standard deviation, that's 72. And I can go over here to the left, and that will be 66. And I can go one more to the left, and that'll be 64. So this is 1 sigma, and this is 2 sigma to the left or right. And this is 1 sigma to the left, and this is 2 sigma to the left. Okay. Now what they want to know is what percent of these adults have heights between 68% and 72. So I want to know this percentage of people. How many people between 68 and 72? Okay. So that's at the 2 sigma, which we know that if I included all of this, this was 2 sigma, right? That would be equal to 95%. 95% of the people would be with all of what I have in blue, but I only have half of that because I'm going to the right of 68. So I need to divide that by 2, and that will be 47.5%. And that was what they asked. So you definitely need to memorize this percentages. 1 sigma is 68, and that is between here and here. 2 sigma is 95, and that's between there and there. And then 3 sigma is 99.7%. Okay. All right. How many of these adults have heights between 64 and 70 inches? So let's, for clarity's sake, continue to draw our normal distribution. We have my mean of 68. The standard deviation was 2 inches. So we can kind of write some our numbers in here, 66, and then we'll take another and we'll go 64. And they want to know between 64 and 70. So now they want to know what percentage of people are between 64 all the way up to 70. Okay. Okay. So what I want to do now is, once again, if 64 is at 2 sigma, and we know that 2 sigma, if I were to go 2 sigma all the way to here, that would be 95% of my data, but I don't have, I only have half of it. And so I have to take 95 and divide it by 2, okay? Then I have 1 sigma to the right, and I know that 1 sigma is 68% of the data, but I only have half of that. So I have 68 divided by 2. So I got to add that together. And if I divide by 2, that will give me 0.815. And they want to know how many adults. Well, this tells me the proportion of people. Okay, so that doesn't tell me how many adults. They actually had 1,800. So I have to take 1,800 and multiply it times that proportion that we just found, and that will give me 1,467 adults. Okay. All right. If one of these adults is selected randomly, what is the probability that this adult has a height of 66 inches or more? So we're going to draw our normal distribution again. We have our mean, which is 68. We know our standard deviation is 2, so we can kind of start filling in these numbers. And we know we have 66 and we have 64, and we want to know the probability that if we selected someone, that we will be above 66 inches or more. So in this blue region, okay? Now, one of the things I didn't talk about is, even though we know that at 3 sigma, it encompasses 99.7%, there's still a little tail worth of data. And so from the average, the mean, all the way to that tail would be a total of that 50%, because that's half of the data. So I know that from 68 all the way up to the max number is 50%, okay? And now I have to, so that takes care of that. And now I have to figure out what portion of this red that I have. So I'm going to take that 50% of the data, and then I'm going to add to it this portion here between 66 and 68. Well, that's 1 sigma. So we know that 1 sigma is 68%, but I only have half of that because it's not to the left and right, just to the left. And so I've got to divide that by 2. And if I add that up, I will find that to be 84%. And that is an acceptable probability. It asked for, oh, wait a minute. What was the question? 84%, yes. Okay, typically probabilities are given in fractions. So 0.84 would be, let's say, a more appropriate response, but a percentage is okay. And so 0.84, or you could have said 84% if they're asking for the probability. All right, want to try one yourself? Okay, welcome back. The scores on a test administered to a prospective employees are normally distributed with a mean of 100 and a standard deviation of 15. What percent of scores are between 70 and 130? So we're going to draw our standard deviation, or normal distribution. We know that the mean is given at 100. We know that the standard deviation is 15. So 1 sigma away, which is 115. And then I got 2 sigma away, which is 130. And then I have, that was to the right. And now I got to go down. So that will be 85 and then down to 70. Those, again, this is 1 sigma. This location is 2 sigma. This again is 1 sigma, and this is 2 sigma. Okay. All right. We know this total percentage of people, or proportion, in blue, that's 2 sigma, is what was that? 95% of the people. And we know that between 1 sigma, left and right, is 68%. Now, what they wanted to know is between 70, what percent of people, or scores, excuse me, what percent of the scores are between 70 and 130, okay? So between 70 and 130. So now we got to find the percent that is this yellow, okay? Right, so how are we going to do that? Well, they are exactly at the distance of 2 sigma to the left and to the right, and based on our empirical rule, we know that that is 95% of the scores are between 70 and 130. If a prospective employee must have a test score of at least 85, what percent of applicants meet this requirement? Well, once again, we know that the distribution is normal. Probably didn't draw that quite good enough. So let's kind of draw a normal distribution. And we know the mean score is 100. We know the standard deviation is 15. So we can kind of fill these in. This is 85. This is 70. And those were 2 sigma. I can go 3 sigma if I need to, but they want to say at least 85. So we're going to be everything to the right of 85. Okay, so this portion in red is 50%, that's half, because now I've not only gone to 3 sigma to the right, I've gone to everything. So I've gone everywhere, all the way to the very last data point, that's 50%. Now I got to figure out how much this in blue is and add it. Well, that is a 1 sigma distribution, and it's not 68% because that would incorporate all of this. I'm only taking half of it, so I have to add 68 divided by 2, and that again will be 84, and they asked for what percent? So there is the answer to the question. So again, you need to memorize, and I'm putting this to memory myself, the empirical rule at 1 sigma, which is to the right and to the left, total, all of that data is 68%, 2 sigma is 95%, 3 sigma is 99.7. Okay. The empirical rule for normal distribution helps with estimations and checking reasonableness of answers, but it is not the most convenient. Let me just see here. I think that's next lesson, so just give me 1 second. Okay, sorry for the delay. This is still part of the lesson. Okay, the empirical rule for normal distribution helps with estimation and checking reasonableness of answers, but it is not the most convenient since it's limited to integral standard deviation values. In other words, values. We want to have something that's been standardized. Since all normal curves have the same shape, it's useful to deal with standardized normal distributions. The most normal calculations will use a value called the z-score, and I'm going to show you how to calculate that. Okay, also called known as the z-values. All right, so we got to understand what the z-score is. A z-score tells you how many standard deviation a value is above, that means it's a positive z-score, or below, that means it's a negative z-score, the mean. Okay, when we interpret a z-score, we will specify the distance, the value, the magnitude of the z-score. It will always be positive. And then we will tell when we interpret it whether that means we are below or above the mean. Okay, so here is the equation. So once again, a z-score tells us how many standard deviations we are above or below the the mean. Okay, the z value for a data, for some data X or some measurement, okay, is a set of normally distributed data given by this equation. So z is the value that you have minus the mean divided by the standard deviation, okay, where mu again is the mean and sigma is the standard deviation. All right, so let me show you how to calculate some z-scores. So if SAT scores are approximately normally distributed, which they are, with a mean of 1068 and a standard deviation of 204, find and interpret the z-score for that. All right, so let's use our equation. So we're going to find the z-score for this situation. Find and interpret the z-score with a student who has a measurement of 1300. So there's my x value. So x in this case is 1300. That is the value that we're being asked for. And 1300 minus the mean, and the mean in this situation was 1068, and the standard deviation was 204. And if you plug that into your calculator, you will get the value of 1.4. So find and interpret. So here's how you would interpret that. the standard, I'm sorry, the student with an SAT score of 1300 has a test score that is 1.14 standard deviations. Now, so this is a positive number, and even if it was negative, we're still going to report it as positive. We have 1.14, and because it's positive, it is above the mean, and we can actually say that test score of 1068. Okay, so the student who has a SAT score of 1300 has a test score that is 1.14 standard deviations. So this has given us our standard deviations above, that's because it came out positive, the mean test score of 1068. So let me give you a situation where we'll get a negative one. We have an iron mine. Large trucks carry iron ore from the mine to the process facility. The amount of iron ore carried by each truck is normally distributed. It has a mean weight of 380 tons, a standard deviation of 5 tons. Find and interpret the Z-score for a truck that carries 373 tons. So the equation for the Z-score is the measurement of interest, which was 373 tons of iron ore. We have to subtract the mean, which was 380, and we have to divide by the standard deviation, which was 5. And if I calculate that, I will find my Z-score to be negative 1.4. Now I'm below, I'm 1.4, 1.4 standard deviations below the mean, okay? So I have an iron ore truck that is carrying 373 tons of iron ore. Is they're carrying a load that is 1.4, always positive, standard deviations, but now we describe the direction. The negative tells me that I'm below the mean. What was the mean? 380 tons. Okay, so we will interpret this. This is 1.4 standard deviations, and it is 1.4 standard deviations below the mean because it came out negative. All right, we got one more to go. Yes. Why don't you try one yourself? The weights, welcome back. The weights of the packages of sandwich meat are normally distributed with a mean weight of 16.05 ounces, a standard deviation of 0.02 ounces, okay? Find and interpret the Z-score for a package of sandwich meat that weighs 15.99 ounces. So my X value in that equation is 15.99. I want to know what is the standard deviation, the standardized standard deviation for this package that has 15.99. I would calculate my Z-score. It is 15.99 minus the mean, which was 16.05. And I would divide that by the standard deviation, which is 0.02. And if I plug that into my calculator, I would find that to be -3. And I would say the package of sandwich meat with a weight of 15.99 ounces has a weight of 3. Always, we're going to describe it as it's positive when we describe it. Standard deviations. Now the negative tells us the direction, which is below the mean weight of 16.05 ounces. Okay. All right. I hope our lesson makes sense. We're going to use z-scores tomorrow to do something very similar that we did up here. And you'll start to see, instead of having numbers on these curves, we will use z-scores. Okay. All right. See you tomorrow.